Thank you, Hassaan. You can take it forward.
Okay, thank you for the introduction. So I'm going to talk about non-supersymmetric closed strings on AdS4, and it's based on these two works, primarily on the first work. So these are my collaborators. Most of the work that I'm going to talk about is done with Ivano and Daniel, who is my advisor. So I'm going to talk about non-supersymmetric strings first and describe what they are. So mostly, we talk about 5 supersymmetric string theories, which are type 1, type 2a, type 2b, and 2 heterotic theories. So these are called supersymmetrics, superstring theories because they do have space-time supersymmetry. But there are more string theories that one can talk about. So let's first talk about what tachyons are. I'm pretty sure that most of you know what tachyons are, but let me just go through them anyway. So tachyons are particles with negative mass squared. And if you have tachyons in your theory, then it signals instability of the vacuum. So that's why they are not desirable. So if your theory has tachyons, then it's a bad theory. Most non-supersymmetric string theories that we know about have tachyons. And this is one of the reasons why we don't study them as often as supersymmetric string theories. But there are some 10-dimensional string theories that don't have tachyons. And one of them is called heterotic O16 cross O16 theory. This is the only string theory which has only closed strings. The other two string theories that we know about, which doesn't have tachyons, are open string theories. So they're called Sugimoto and Sagnoli model. So in this talk, I'm going to talk about this first theory on AdS4. So one feature of non-supersymmetric strings is that you can have one loop corrections to the cosmological constant. So in superstring theories, the loop corrections to the cosmological constant vanished. So the kinds of question that I'm going to ask in this talk, you cannot ask those questions in superstring theories because you don't have the one loop correction. So you can have one loop correction, to the cosmological constant in non-supersymmetric strings, and therefore you can ask some interesting questions. So since loop corrections are present in non-supersymmetric strings, one question that you can ask is that, can you uplift an AdS spacetime to de Sitter spacetime using this loop correction? Now, the second question, sorry, is there a question? No, okay. The second question that I'm going to talk about in this talk is that are non-supersymmetric backgrounds stable, or at least metastable? And by metastable, I mean they're long-lived, even if they're not stable. And when you talk about stability, you have at least two kinds of stability. One stability is against perturbative processes. It's called perturbative stability. How to check for perturbative stability? Well, it depends if you are talking about Minkowski spacetime or AdS spacetime. If you have a Minkowski spacetime, then if all the mass squares of the modes that you have are non-negative, then it means that you have perturbative stability. But when you have AdS spacetime, your mass squares can be slightly negative, but not too negative. So there is a bound on the mass squares that you have, a lower bound, and that bound is negative, and it's called the BF bound. So it depends on if your particle is a scalar particle or a P form, and it also depends on, for example, you can talk about gravitons, for example. So you can see that all of these bounds are negative, and if your mass square is greater than or equal to this bound, which is called BF bound, then you do have perturbative stability. If any of the mass square of any modes goes below this bound, then the perturbative stability is not there. There's another kind of stability which is called the non-perturbative stability, and it means stability under non-perturbative processes. And when I say non-perturbative processes, I mean bubbles like Coleman-Delucia like processes. So if you have bubbles which form under non-perturbative processes, you say that you have non-perturbative stability. And we'll talk about both of these stabilities in this talk. Okay. Now there's a theorem that kind of addresses the first question that I asked about the uplift to de Sitter. So there is a Maldacena-Nunes style no-go theorem that exists due to these two authors, Basile and Lanza, which says that if you have an action like this, right? So you can see that, the first term, the second term, and the last term are usual, terms in the, string actions that we study. This third term comes from one loop correction, and this T is just a constant. So suppose that you have an action like this, and you have a closed manifold Y, where the dimension of Y is Q, and it has to be bigger than P plus 2, so that you can have, this flux on this, space Y. Now, suppose that this flux threads, a P plus Q cycle in Y. Then it turns out that de Sitter and Minkowski vacuua are forbidden if this inequality is satisfied, where this alpha comes from this term, this gamma terms from this one loop correction, and this p comes from the rank of this flux. So if this particular inequality is satisfied, then you can't have de Sitter and Minkowski vacuua. But you can see that this thing only has a flux on the internal space y, which means that you have magnetic fluxes only. If you have an electric flux and magnetic flux, then this theorem doesn't directly apply. Okay. Now, there have been some backgrounds that have been studied in the past. So one background that has been studied is AdS3 cross S3 cross S3 on a string scale S1. So you can say that it's AdS3 cross S3 cross S3 cross S1, but S1 is a string scale, S1, so it doesn't change its radius. Now, there are three fluxes that you can put, three H3 fluxes, because you have three, components with a dimension of 3. So two magnetic fluxes on each of S3, and one electric flux on AdS3. Now, if you have this setup, it turns out that there is no uplift to de Sitter. So it was checked by Beccara, Robbins, and Setti in this paper, and this background was studied in detail in this paper by Grania and Fryman and Setti. Now, another thing that this first paper checked is that you do have perturbative stability when it comes to scalars, at least. They didn't check the perturbative stability for vectors, right? But the question of non-perturbative stability was not checked. Why? Because the moduli space for S1 is a bit complicated. So you have to check if there is some non-perturbative process that you can have in the moduli space of S1. So that's why it was not checked. Another background that was studied is this background by myself and my advisor last year. So again, you have two components with dimension 3. So you can put one magnetic component, one magnetic flux on S3 and one electric flux on AdS3. Again, the uplift to de Sitter doesn't happen. And the perturbative stability of scalars, again, it was checked, and it was checked that they were above the BF bound. So there was no perturbative stability. Again, non-perturbative stability was not checked because you have a T4. So torus moduli for T4, torus moduli space for T4 was quite complicated. So one thing that we can see in both of these examples is that the question of non-perturbative stability becomes hard because you have a torus moduli space. So why don't we study a background that has no torus moduli? And that motivated us to study AdS4 cross S3 cross S3 because you don't have any torus moduli here. So at least we can study, the question of non-perturbative stability here. So there is no torus moduli, and non-perturbative stability is easier to study. And one interesting thing that this background has is that it has inverse scale separation. We'll see what this means in a minute. Okay, now let's talk about the first question. So let's start from the 10-dimensional action of the O16 gross O16 heterotic theory. These are the usual terms that you see in string action. This is just the field strength for heterotic gauge theory, a heterotic gauge field. Now, I'm going to take this metric on AdS4 cross S3 cross S3, where these chi's are just the volume moduli for the spheres. And these components, these d omega 3 squares, are metrics on the two S3s with radii L and L tilde. So these are not unit spheres. Okay. Now let's write down the potential that you will get, and you will get, a term from the, curvatures of S3 and one term from, the fluxes on S3. So when you write down the potential, you get something like this, where this curly V is just a combination of the three moduli. Now, what we have to do is that we have to take the derivatives of this potential and set them to 0 and solve for L's. And let's see what happens. When you write down the derivatives and write down the equations, I'm not going to write down the equations because that's not important. It turns out that the equations are inconsistent. So you can't solve the equations. There is no solution to those equations, which means that no tree-level solution exists for this background. So one thing that we can do, as I said before, is to add one loop corrections. Now, I'm not going to derive this one loop correction, but I can tell you that it looks like this. So it looks like this lambda is just a number that comes from the integral of the one loop partition function over the fundamental domain. Apart from that, the other things we have seen before, this GS is just the one loop corrected G string. Okay. Now, total potential is the tree potential that I wrote earlier, plus this one loop contribution. Now, if you add this one loop contribution, do you have a solution now? And it turns out that yes, if you take the derivatives, you get these equations and you have a solution, but it's hard to write it down. Well, you cannot write it down in analytic form, so you have to use numerics, but the solution does exist. So you can plot it at least. So there are four things that we can plot. One of them is L, which is the radius of one S3. The other thing is the other L. Sorry, do you have a question? No? Okay. So the other thing that you can plot is the other radius, and the third thing is your potential itself. So if you plot, the radius of one S3 with versus the flux on that S3, you can see that as you increase the flux on that S3, the radius increases. But if you increase the flux on the other S3, it comes to a constant value. And the same thing happens with the other radius. If you increase the flux on the other S3, the radius increases without bound. But if you increase the flux on the other S3, it comes to a constant value. You can also plot G string, and it turns out that G string goes to a constant value. I mean, it's not easy to see from here, but it turns out that for small fluxes, this G3 goes to a constant value. So it doesn't increase without bound. That's what I'm trying to say here. So it goes to a constant value if you decrease the flux. And if you increase the flux, it goes to smaller and smaller values until it goes to a constant value. If you plot the minimum of the potential, you can see that the minimum of the potential increases as you increase the flux, but it never becomes positive, which means that you don't get an uplift to de Sitter. And the minimum of the potential is always negative, which means that you always have an AdS solution, even if you add the one loop correction. So this happens for both of the fluxes. And if you plot the AdS length scale, you see that if you increase either of the fluxes, it goes to a constant value. But if I remind you from the first two graphs that I showed you, if you increase the flux on the first S3, the radius of that S3 increases without bound. If you increase the flux on the other S3, again, the radius of that S3 increases without bound. But we can see that the radius length scale goes to a constant value if you increase either of the fluxes, which means that the size of one S3 is going to be bigger than the size of the AdS, no matter what flux you increase. Therefore, we say that this background has inverse scale separation, which means that one of the internal space components is going to be bigger than the Lorentzian component. Okay, so the uplift to de Sitter doesn't happen. So we didn't get the answer to the first question. One thing that we can notice is that, and it's going to be useful later, is that the solution, whatever the solution is, we cannot write it down as an analytic form, in the analytic form, but we do know that if you do this rescaling, then the solution is invariant, which means that if you have a quantity that is invariant under this rescaling, that quantity should only depend on the ratios of fluxes and radii. So as I viewed before, that you always get an AdS solution. So you can write down the expression for the AdS length scale in terms of the two radii. One interesting thing is that if two of the fluxes are equal, then you can write down the analytic solution. And it turns out that both of the radii are equal, and they're given by this expression. GS is given by this expression, and the AdS length scale is of the same order, but it's a bit bigger than either of the radii by a factor of 1.5. Okay, so that concludes the section for uplift to de Sitter. Now let's talk about the other question, which is about the stability analysis. Sorry. So for stability analysis, I'm going to write down the action, but now I also have a one loop contribution. And you can see that I have dropped the term for F2 because there are no F2 fluxes in our construction. So you can start from this action and you can write down the equations of motion. And these are the equations of motion, where this lambda is just this one loop correction. So it's a bit confusing. This lambda is not the cosmological constant. It's just one loop correction to the action.
Sorry. Sorry, before we proceed, can you just go back to the last slide?
Last slide, okay.
Here,
yeah.
How did you get the expression for the AdS length scale in terms of the sphere length scales?
So AdS length scale for AdS4 is given by -6 over the minimum of the potential, right? So what you do is that Hey, wait, give me a minute. So you take the expression for the tree level potential, which was given here, here, and you add to it this one loop potential. So you get the full potential. Now, if you have the expression for this full potential, you use these equations of motion to simplify the expression, and it turns out that you can write it down in terms of the two radii only, right? L and L tilde. And as I told you, that AdS length scale is just -6 divided by the minimum of the potential. So if you're using these equations of motion, it means that the potential that you have is the minimum of the potential, because at the minimum of the potential, you should have these equations. So that's how we derive the minimum of the potential. And yes.
No, I mean, it's clear. Thank you. Yeah.
Okay.
Yeah.
Okay, let me go back. Okay.
So I had a small question.
Mm-hmm.
So here you're making the one loop correction compete with the tree level one, basically for the minimum of the potential. But can you guarantee that the other subleading perturbative corrections are actually subleading? Because
Yes. So the thing is that, sorry, is your question over?
yeah.
Okay. So the previous background that I mentioned, one of the previous backgrounds was AdS3 cross S3 cross D4. So in that paper, we did have some scaling arguments that showed that if you have more, higher order corrections, they should be subleading, right? So I think that same argument can be made for, this construction, that, if you have higher order corrections, they should be subleading. And so the thing is, one thing that I didn't mention, and I should mention it, is that if you go back to this one loop potential, one thing that I didn't mention, although it's written here, is that it's approximated by R1, 9. So this partition function that we are using is actually not the partition function on AdS4 cross S3 cross S3, because that will require us to write down the Voltsheet theory on AdS4, which is hard, right? And S3 and S3. I mean, they are easy, but AdS4 Voltsheet theory is hard to write down. But if all of these components are big as compared to the string scale, you can approximate AdS4 cross S3 by R1, 9, right? And you can also see that, well, for all the fluxes, these components are not going to be arbitrarily big enough as compared to the string scale, which means that the conclusions that we have, they only hold for a certain range of the fluxes, right? Now, the scaling arguments that I mentioned before, they show that the conclusions that we have made in a particular range of the fluxes, in that particular range of the fluxes, they are going to be valid even if you include higher order corrections, right? So you can't say anything about the range of the fluxes where all of these components are not big anyway. So we don't have to worry about that range of the fluxes at least. Does that answer your question?
Yeah. Can you go to a slide in the front, like maybe one or two?
Which slide?
Maybe in the front, let's say 2021 or something.
2020. Okay.
Yeah, exactly this one. 20.
This one?
So let's say you're competing the tree level with the lambda correction, which is the one loop one. So lambda should take on a bigger value just to compete with the ones at tree level, right?
Yes.
So basically it's a bit naive question. How can you neglect lambda squared correction?
Well, as I said, that we do have some. So we do have some scaling arguments. I mean, I can refer you to the. I mean, I can after the talk, I can even refer you to the section that I'm talking about. The thing is that you can show that the higher order corrections do produce us. So here's the thing. So the lambda is not as big as the other thing, because if it was big enough, then we would get an uplift to de Sitter. So you can see that one of the reasons why we don't get an uplift is that lambda is not big enough, right? If it was, because lambda is positive. So if lambda was big enough, we would get a de Sitter uplift. I mean, it's not as big as that it can take us from a negative V minimum to a positive V minimum. So it's not as big as the tree level, I would say, but it's kind of big enough that it competes with it to uplift it to a certain negative value, but not big enough that it can take you to a positive value. So I don't think that it's as big enough as the tree level potential.
So it doesn't give you a runaway, basically.
It doesn't give you what?
Some runaway like thing.
I don't think so. No. But I'm not sure about that. But I don't think so. It doesn't give you that. No. Okay.
Yeah, thanks.
Okay. So I was here. Okay. So these are the equations of motion that you get from the 10-dimensional action. Now we're going to talk about AdS3 cross S3 cross S3. And we're going to talk about the solutions with zero dilaton, right? Because this dilaton is actually the fluctuation in dilaton. The vacuum expectation value of dilaton is actually absorbed in this kappa 10. So with zero fluctuation of the dilaton, these are the expressions for the Ricci tensor for, I think this should, yeah, okay. So this R mu nu means that you are on AdS4. This RAB means that you are on the first S3. And Rij means that you are on the second S3. And the mixed Ricci tensor components just vanish. The full Ricci tensor is just the sum of these three things contracted with their matrix. And the background H3 that we're going to take is going to be on these two S3s because you can't put any H3 on AdS4. So this is the H3 that lives on the first S3, and this is the H3 that lives on the second S3. And these curly L's can be written in terms of the radii of these spheres and the one loop correction. Okay. Now we have to introduce perturbations. So we introduce a perturbation in the dilaton, but since the background dilaton is just zero, so we're gonna call the perturbation as phi only because the background phi is zero anyway. Now in the metric, we're gonna introduce some perturbations, and we have to divide our cases based on what component you are on. So you can either be on AdS4 or the first S3 or the second S3, or you can have mixed components like this. And since we know that the mixed components were zero, therefore the perturbations are quite simple here. For AdS3 and the other S3s, we have divided our perturbation into a traceless part and a trace part. For example, here H mu nu is the traceless part, KAB is the traceless part, and K tilde is the traceless part. Similarly, for the B field, we're going to introduce some perturbations like this. Okay, if you introduce these perturbations, you also have to talk about fixing the gauge because you have some gauge freedom. So we're going to choose some Lorentz-like gauge conditions, and the gauge condition that we choose is that any component that has an A or B in it, which means that it lives on the first, it has one component on the first sphere. If you contract that with in nebula A, that should be zero. And you do it for all of these components that have a single A or B in it. Now you can translate these gauge conditions in terms of these perturbations. And it turns out that all of these things should be zero, right? Now, you can write down the equations of motion. I'm not going to write them down because they're quite ugly. But after you write down the equations of motion, you have to break them into spherical harmonics. So you have two spheres. You can write down any function on these spheres as a linear combination of spherical harmonics over these two spheres. So we're going to talk about spherical harmonics here, which are y's, and then vector spherical harmonics, which are called YAs, and tensor spherical harmonics. And they satisfy some useful identities. I mean, I can just write them down here. I mean, we won't be going through derivations, so we won't be needing them, but you can see that these are some of the, identities that they satisfy. Okay. So you can break down your equations in spherical harmonics. Now I'm going to show you that how different kinds of fields break down in spherical harmonics, just to give you an idea of what the equations look like. So if you have a field that has no components, the breakdown is pretty simple. You just have these modes and multiplied by the corresponding spherical harmonics. If you have a single component living on a sphere, which is A, which means that you have a single component on the first sphere, you can have three different kind of terms. One term includes a vector spherical harmonic with an upper index that says 1 with L. One term has the vector spherical harmonic with -1 in the superscript. And the last term contains the derivative of the scalar spherical harmonic. So you can have three kind of terms here. If you have two components on the first sphere, then you can have even more terms. I mean, all of the terms that can happen, I'm writing them down here, or writing them down here. Now, the last thing that can happen is that you have one component on one sphere and one component on the other sphere. Then you have a lot of terms. You have like 9 terms, right? And I have written all of them here. So you can get an idea that if you break down your equations of motion in spherical harmonics, it's going to be really, really messy, right? But it's going to be useful because we can study different kind of modes then. So the gauge conditions now translate to these nine different conditions. You can see that we have different conditions for different modes now. But the thing is that even if you impose the gauge conditions, it doesn't fix all of the gauge freedom that you have, because you do have some residual gauge transformations that you can still have. But you have these residual gauge transformations only when L and L tilde are equal to 0 or 1, right? Which means that we have to treat these cases with caution. So it means that we're going to talk about 3 different cases at least, when L and L tilde are equal to 0, or, sorry, 2 cases, when they're either 0 or 1, and the other case is when both of them are greater than or equal to 2. So if we divide all of the cases that we have, there are 6 different kind of sectors. One sector is when you have this thing, which means that the first sector has a 0 here, and the second sector has plus or minus 2. And the other sector is going to be when one of the sectors has plus or minus 1 here, and the other sector has a plus or minus, but this prime means that this sign is independent of the first sign. So it means that this is actually 4 sectors. And I have written down the other sectors as well. I'm not going to go through all of them, but there are 6 different kind of sectors. But in each kind of sector, you have to be cautious about if L or L tilde is equal to 0 or 1. So for example, if I take this sector, L0, L0, there are 9 sectors that one can write down based on if L is equal to 0, 1, or greater than or equal to 2. So if you write all the sectors for all of these all the cases for all of these sectors, it turns out that there are 31 different kind of sectors to study. Now, of course, I'm not going to go through all 31 different sectors because that will take a lot of time and they're not interesting anyway. So I'm going to go through some of the sectors which are interesting. So it turns out that in these 4 cases, in these 4 sectors, you don't have any negative masses, right? Which means that all of the masses are either 0 or positive. But I remind you that the BF bound that I mentioned at the start, all of the BF bounds were negative, which means that if there's a sector where the mass squares are non-negative, then there is no chance that they're going to violate the BF bound, which means that the BF bound violations are absent in these sectors. So if these 4 sectors are eliminated from the candidates that can violate the BF bound, it leaves only 2 sectors. One of the sectors is this, and the other sector is this L0, L0. So we're going to only investigate these 2 sectors. Okay, so let's investigate the first sector. Now in this sector, you can write down the equations for everything, scalars, vectors, and tensors. Now it turns out that the vectors and tensors, they don't give you any equations that can be problematic. But there is one set of equations, which I have written down here, that is problematic. So let me show you how to derive m squares from these equations. You can see that these equations come in the form where you have a Laplacian, the Laplacian, acting on a vector, because these 2 equations can be combined into a vector. And the vector has W and P. And on the right-hand side, you have a matrix that has entries, this bracketed term, this bracketed term, this bracketed term, and this bracketed term, acting on the same vector. So you have a Laplacian acting on a vector that has W and P equals a matrix multiplied by the same vector. So if you take that matrix and calculate its eigenvalues, those eigenvalues give you the mass squares. So since you have a 2 by 2 matrix here, you have 2 eigenvalues. And I have written those 2 eigenvalues here. And you have an additional sign here. I have written a double prime here because you have 2 signs here. One sign comes with a prime. Therefore, to differentiate this sign with this sign, I've given it a double prime. So you can see that the first sign comes here, the double prime sign comes here. So you have two eigenvalues here. Now, it turns out that if you have L and L tilde both equal to 1, and these two signs are opposite of each other, then you have a problem. So as I said, if you have L and L tilde equal to 1, and these two signs are opposite of each other, sorry, not these two signs, actually these two signs are opposite of each other, then you have M minus, sorry, what? No question, okay. So if you plot M minus squared, which means that this double prime sign is negative, it turns out that it does violate the BF bound. So you can see that if you plot it with respect to the flux ratio, it does violate the BF bound when the logarithm of the flux ratio is 0 and in the neighborhood of that point, which means that when the fluxes are almost equal to each other, you do have a BF bound violation, and this violation goes away when the one of the fluxes is bigger than the other one, much bigger than the other one. So this blue line shows you the BF bound. And you can see that there's a violation when the two fluxes are almost equal to each other. So there is a problem now. But you can see that since this this violation only happens when L and L tilde are equal to 1, it means that you can remove this problematic mode if you replace one of the spheres by the three-dimensional projective plane. Because what happens is that if you replace a sphere by a projective plane, it removes all the modes with odd L's, right? And L is 1, which means that L is odd. It means that if you remove any of the spheres and replace it with a projective plane, it's going to remove. So suppose that I remove the first sphere, first S3, and replace it with a projective plane, RP3, right? Then L equals 1 sectors are going to disappear. They don't exist anymore, which means that this mode is going to, this mode will disappear. It's not going to exist anymore. So this problematic mode is here, but it can be removed if you replace any of the spheres with a projective plane. So that's good news, at least. Now let's talk about the other sector that we didn't mention before. Now in this sector, as I showed you earlier, that there were 9 cases that you can study. You can study all of those 9 cases, and it turns out that there is no BF bound violation in any of those 9 cases. So I can show you the graphs for all of these 9 cases, and you can see that all of these graphs are either strictly positive, but some of those graphs, although it's hard to see, they do become a bit negative. But I can tell you that none of these graphs violate the BF bound. So these are 3 graphs, there are 3 more, and here are 3 more. So these are all 9 cases that I discussed earlier. So there is no BF bound violation in any of these, subcases, which means that the only BF bound violation comes from this sector, and it can be removed if you replace any of the spheres with RP3. So that's good news, at least. Okay, so let's talk about non-perturbative stability now. Give me a minute, let me drink some water. Okay, so non-perturbative stability happens because of non-perturbative processes, and the process that we're going to study is called brane nucleation, which means that you have a brane that nucleates somewhere, and it starts to expand as a bubble, right? And as it expands, it reduces the flux inside, this bubble, and the flux outside is unchanged, of course. But this brane, this bubble expands and expands, and it reduces it gives you a background with a smaller amount of flux, right? So that's why I have written here that branes reduce the flux in the background. So this is easier to see in a one-dimensional example. Suppose that you have, a one-dimensional space and you have some external electrical field, right? If there is a particle-antiparticle pair, although it's hard to see, but this particle is positively charged, and this particle is negatively charged. So if you have a particle-antiparticle pair, the electric field between this particle-antiparticle pair is going to reduce. So internal electric field, which means that the electrical field between these two particles is going to be smaller as compared to the external electric field. And as these particles go away, if suppose that the distance between them is, r2 times r, then it turns out that the internal electric field is actually external electrical field minus this thing as r goes to infinity. Because if r is not infinity, then it depends on where you are on space-time. But as r becomes much bigger, um, then it goes to this particular thing. But the moral of the story is that the internal electrical field becomes much bigger. Sorry, can become smaller as compared to the external electrical field. So this is a bit like reducing the flux because of a particle-antiparticle nucleation. But one thing that you can see is that these particles are going to go away from each other only if their electrical charge is bigger than their mass in appropriate units. So which means that you have to have particles where you have charge bigger than mass. And it does point to weak gravity conjecture, because this is kind of what weak gravity conjecture says from the swamp land. So similarly, for our case, you need to have something called NS5 brane. Now, NS5 brane has 5 dimensions of space and 1 dimension of time. So it's gonna appear as a 2-dimensional surface in AdS4, which means that it has 3 dimensions which needs to go somewhere. So those 3 dimensions wrap a 3 cycle on S3 cross S3, right? Any 3 cycle. So I'm gonna write down a 3 cycle on S3 cross S3 as A times any cycle that wraps S3, the homological class of that, plus B times the homological class that wraps the other S3. Now, before I proceed, you can see that this NS5 brane, and which appears as a 2-dimensional surface in AdS4, it can expand, but there are 2 things that you have to consider here. One thing is that it has a tension, and that tension is trying to make it smaller, and the other thing is charge, and the charge that it has, and that charge is trying to make it bigger. So if the charge wins, then it's going to expand. If the tension wins, then it's not going to expand. It's going to come as it's going to it's reduce in size. That's what I'm trying to say. Which means that you have to have some branes that do satisfy the weak gravity conjecture for branes in order for this to happen. Okay. Now, if I define beta as the charge over tension ratio for this NS5 brane, decay happens when beta is bigger, which means that charge is bigger than tension, as I just said. So for semi-classical approximation, so we are using a semi-classical approximation here. So for semi-classical approximation, beta has to be of order 1, because if tension becomes very small, or if tension becomes very small, then it breaks down. So we need to have 2 things in mind. Beta should be of order 1, and for the decay to happen, beta should be bigger than 1. If it's smaller than 1, the decay doesn't happen. If it's equal to 1, that's a tricky point. But if it's bigger than 1, the decay certainly happens. And the second thing is that if beta is not of order 1, then we can't trust our calculation because the approximation doesn't work. Okay. So one can calculate beta by calculating charge and tension. For tension, you need to have the dBi action. For charge, you need to use the Stokes theorem. So you can calculate both of these things. And we have done that in our paper. So the result is this. This is what you get for beta. Now, A and B are these 2 integers that I mentioned here, A and B. And N and L tilde are the 2 fluxes on the 2 spheres. I told you what L and L tilde are. They are the radii of the spheres. And LA is the AdS radius. So this is the expression for beta. Now, one can write this down in terms of ratios only. So if we define 3 ratios, xi, which is the ratio of radii, zeta, which is the ratio of A and B, and mu. Now, this third ratio is not independent of the first 2 because you can write it down in terms of xi. So let's ignore this flux ratio. So you can write beta in terms of xi and zeta quite easily, which means that this thing only depends on the ratios. Okay. Now, what we're going to do is that we're going to write down beta. So we maximize beta with respect to zeta for a fixed xi, which means that we have to find what cycle. So when we are finding zeta, which it means that we are trying to find what cycle should you wrap on S3 cross S3 for a given set of ratios, for a given set of radii. So for that, we need to maximize beta. Why do we need to maximize beta? Because if the maximum beta is not greater than 1, then of course the decay is not going to happen. So therefore, we only care about the maximum beta. So we're going to maximize beta with respect to xi for a given ratio of the radii. And it turns out that this maximum value depends on if the xi is greater than 1 or less than 1, which means that is one radius of the sphere bigger than the other radius. So it turns out that the expression for beta max depends on if xi is bigger than 1 or smaller than 1. So for non-perturbative decays, you can plot actually. You can plot beta with respect to xi, and I can give you the plot. It's here, right? And the plot, you can see that the plot brings you to a point where, so you can see that on the horizontal axis, I have arc tangent of the flux ratio. And the minimum value happens when you have something like 0.707. And 0.707 means that you have, the two fluxes equal to each other, because 0.707 means that the tangent is equal, arc tangent is equal to 0.707, that which happens when the two fluxes are equal to each other, which means that n tilde over n is actually equal to 1. So the non-perturbative decay brings the configuration to a point where the fluxes are equal to each other. And if I bring you here, it means that mu is equal to 1. And you can solve for xi. It turns out that if mu equals to 1, that xi also has to be equal to 1, because you can see that if xi is equal to 1, then this thing is 1, right? So therefore, I'm saying here that the non-perturbative decay brings the configuration where xi equals to 1, which corresponds to equal fluxes. And if you have equal fluxes, you can see what the value of beta is. Just put xi equals to 1 here, and it turns out that beta is equal to 5 over 2, which is of the order of 1. So our approximation doesn't break down. If it's of the order of 1 and it's bigger than 1, which means that the decay does happen. It means that the non-perturbative decay always happens, and it brings you to a configuration where the two fluxes are equal to each other. But the interesting thing here is that if I remind you, then the BF bond violation happened when the two fluxes are equal to each other. So we are kind of a pickle here. If the fluxes are equal to each other, then you have a BF bond violation. But if they are not equal to each other, the non-perturbative stability, is very bad here. I mean, you have extreme non-perturbative processes that bring you down to a point where the fluxes are equal. But when the fluxes are equal, you have BF bond violations. So in order to get out of this pickle, you have to replace one of the spheres by RP3. Because if you have RP3, then this problematic mode goes away. And therefore, the non-perturbative decays bring you to a point where the two fluxes are equal. And if one of the spheres is replaced by RP3, then you don't have a problem anymore. Okay. So this is, the structure for non-perturbative decays, via brane nucleation. Now I'm going to talk about some future directions. So one future direction is that how to study non-perturbative decays when you have torus moduli. So the background that we studied here, it doesn't have torus moduli, because if you have torus moduli, then you also have to worry about tunneling in the torus moduli space, which can be a notorious problem to study. So some backgrounds that we want to study are the backgrounds that we studied previously. For example, AdS3 cross S3 cross T4, and the other background that I mentioned. And what about this background, AdS3 cross S3 cross K3? So the one point in the K3 moduli space is just T4 over Z2. So at least we can study that, because we already know the results for AdS3 cross S3 cross T4. So as I said, that tachyons are removed, which means that the modes that violate the BF bound, they are removed if one of the S3s in AdS4 cross S3 cross S3 is replaced by RP3. So if you don't have tachyons, then you can at least start talking about the holographic picture. So what is the holographic picture for this background? That's one thing that we need to study. And the last question, and it's a bigger question to study, is that can we make general statements about the stability of backgrounds like AdS cross anything? I mean, the backgrounds that do make sense. And this has to do with the Oguri-Waffa conjecture, which says that the non-supersymmetric AdS spacetimes cannot be stable. So if we have enough, backgrounds under our belt, and we do know the patterns for their stability properties, then we can hope to make some, statement about the stability properties of, AdS cross anything backgrounds for non-supersymmetric strings, at least for the closed strings. So that's it. Thank you for listening.
Yeah, so in the case where you replace one of the spheres with the projective space, are there other potential instabilities that you have to worry about, or would you claim that it's stable?
So I don't think that there will be any instabilities, but one thing that I was a bit concerned about is that, so if we haven't worked this in detail, but it seems, I mean, I don't think that there is going to be any instability that will be introduced. But one thing that I'm a bit concerned about is that the volume of one of the spheres will change, right? Which means that the analysis for non-perturbative stability will change because it does depend on the volume of the spheres, right? But we do think that me and my collaborators think that what will happen is that the value of beta will change by a factor of 2 or something, which still makes it of order 1. So I think things should be fine, but we're not aware of any instability that will be introduced.
So, I mean, if I just go back to your first sections of the presentation, then you found this solution by minimizing the potential in your 4-dimensional vector field theory.
Wait, give me a minute. You're talking about this slide? Sorry, this slide?
Yeah. So I just wanted to see what are the moduli that you're taking into account.
So the moduli that we are, sorry, please complete your question.
Please go on.
So your question is that what moduli am I differentiating with respect to?
Yeah.
Okay, so the moduli that I'm differentiating with respect to are the dilaton and the 2 volume moduli. Because the thing is that the spheres have only one modulus, which is the radius modulus. They don't have any moduli space apart from that. So the only modulus for the sphere is the radius modulus that I'm calling xi and xi tilde for 2 spheres. And the other modulus is the value of the dilaton, and that's it.
Nice. And
yes.
Also, I mean, so your n and n tilde reflects the fluxes, right?
Yes.
Okay. So you said that once you tune these fluxes, you can change the size of these S3s, right?
Yes.
So are all the values of those fluxes solutions, or only one of them is a solution?
No. So there is a solution for any pair of n and n tilde. I mean, so one comment that I made earlier was that the approximation that we made here, that the partition function that we are using is actually a partition function for R1,9. That approximation will only be valid if all of the components, so by which I mean AdS4 and S3 and F3, they are much bigger than the string scale. Which means that if you have a flux configuration where one of these components is very small, then this approximation is going to break down. But if you accept this approximation once, then any pair of fluxes gives you a solution.
So you have a family of solutions, basically.
Yes.
A parametric solution.
Yes.
Also, one more line question. You're trying to find the masses of these 3 scalars, right? In your second section.
I'm sorry, I don't understand by masses of these 3 scalars. Which scalars?
You're looking for whether the masses violate BF bounds. Are you trying to find masses of these 3 universal moduli or some other things?
I'm sorry, there's some noise in the background, so I can't hear you. I mean, in my background, not your background. So let me rephrase your question. So your question is that I'm trying to find masses of these 3 scalars. Is that your question? Okay. So it turns out that these 3 scalars, they we have a solution when these 3 scalars are set to 0, as I said here, and it turns out that you have a minimum of the potential here. Yeah. So I don't think that we're trying to. Well, yeah, sorry, what?
No, I'm just asking, what are those masses of? You found you were analyzing several masses.
Oh, okay. Yes. Okay. So they are the masses of. So they are the masses of the perturbations actually that I introduced. These perturbations. So these perturbations may not give you a good mass matrix. So therefore, what you can write is that you can write on the mass matrix, and you can find the eigenvalues of this mass matrix. So when I find the find the masses, I'm finding the masses of all these perturbations. So I'm starting with the background solution. So this is the background solution, and I'm perturbing it in the space in the moduli space. And if you perturb this background solution, it will give you a number of modes, right? And what are the masses of these modes? That's what I'm investigating, not the masses of phi, chi, and chi tilde.
Yes.
So these perturbations, yeah.
Thanks. Good. Next.
I had one question. So can you go back to the very last slide of perturbative stability?
Perturbative, okay. Here,
Next section.
next section, non-perturbative, okay.
Perturbative stability. Sorry.
Okay, no problem. Here
Maybe
or
one.
here?
Yeah, maybe one before.
This one?
No, before. Back.
Before here? Yes.
Okay, so I'll just ask anyway. Why did you want beta to be much greater than 1?
Not much greater than 1. No, I don't want it to be.
Why you didn't want beta to be much greater? What is the problem with that? I missed.
So I want my beta to be greater than, sorry, I don't want my beta to be greater than 1, by the way. I'm just giving you a criterion that if beta is greater than 1, then the decay happens, because that will mean that the charge is bigger than the mass, right? But I don't want my beta to be much greater than 1, because if it is much greater than 1, then it means that the tension is very small or charge is very big. And in those cases, the semi-classical approximation that we use, that breaks down. Because then you have to talk about other effects that we didn't take into account, like the back reaction or something like that. Actually, this analysis is not different from the analysis that has appeared for some Freund-Rubin solutions. For example, there was this work done by one of my collaborators, Ivano, for his PhD, and the same analysis goes there. And in that analysis, again, he doesn't want beta to be much greater than 1 because the semi-classical approximation breaks down.
Okay, so maybe we can thank Hassaan.
Okay. Thank you for the invitation.
Thank you.
Maybe stop the record.